Okay, now I'm far above Mr. Burke now, looking down at a whiteboard that has some words on it. And what Mr. Burke's going to do is sort of help us understand how to convert from these grams to these moles, to molecules, and atoms.
Right. And in the course of study, we're going to be interested in grams and molecules and relating them back to moles. The thing is, we can't go directly from grams to molecules, so we're going to figure out a way to relate the two. If I'm given a mass, and we'll say 22 grams, and I want to figure out how many molecules I have, I'm going to first have to figure out how many moles I have. And to do that, I just use dimensional analysis, just like we did when we were doing metric conversions. So the dreaded T-chart is back, just like I told you it would be.
It's not too dreaded.
So we know that we need to convert grams to moles. And we know the relationship between 1 mole and the mass of that compound is the molar mass. And from our earlier discussion, we know that CO2 has a mass of 44.01 grams. So if we put our conversion factor, 1 mole, over the 44 grams, we can cancel out the grams and end up with moles. In this case, keeping math very simple, we have 1/2 mole of CO2.
So it's pretty darn important to cross those units out, right?
Exactly. And it's really easy to see that if we had put this in backwards, we would have come up with a crazy unit that wouldn't make any sense, would have had grams times grams, or grams squared.
Which doesn't really mean anything.
No, it doesn't. We've had a square meal, but square grams don't count. All right? But this 1/2 mole isn't giving us all the answer. We wanted to know how many molecules that 22 grams had. So it turns out we have to relate that 1/2 mole to molecules. And we know the relationship between molecules and moles is Avogadro's number. So to take that information, the 0.50 moles, and put that into our T-chart, 6.022 times 10 to the 23rd molecules over 1 mole. And again, our moles cancel out, and now we just multiply, right?
Right.
And so we come up with 3.011 times 10 to the 23rd.
Exactly, half as many molecules.
Exactly.
And it seems like the mole is sort of the grand central station of the whole thing.
It is. It is. And if we go back to our little display here, we can think about, if we're going, we know the relationship between grams and moles is molar mass. And if in a few minutes we're going to give you a mole house, which is a graphical organizer that helps us to see that. And if we're going from moles to grams, if I'm give you a number of moles and ask you to figure out how many grams that is, we simply multiply the number of moles times the molar mass. If I give you grams and ask you to find out how many moles there are, so I'm going in that direction, all I have to do is divide by the molar mass. Okay? We have a relationship here between molecules and moles as well. We said that was 6.022 times 10 to the 23rd. And
Avogadro's number.
Avogadro's number. And I'm going to kind of mess this up as I write this down.
Nice job.
But again, we can do the same thing. If we're going from moles to molecules, so we're going in this direction, we're going to multiply by Avogadro's number. If we're going from molecules 2 moles, we're going to divide by Avogadro's number.
That sounds pretty straightforward there.
Really, it does.
And you have a nice little pathway from grams to molecules.
Exactly. And when you look at the graphical organizer, we're going to see that we've got a lot more that we can add on as we continue forward in our study of chemistry.
You have at the bottom there atoms, so what about that?
What about that? Well, what do we know about atoms and molecules? Think back to what we talked about when we first started figuring out what the atomic mass was, the molar mass was. We looked at the molecule, we counted the atoms. So we could go from molecules to atoms, multiplying by the total number of atoms, or the number of atoms of any one particular type of element that's in the compound.
So it would be determined by the type of molecule you're really looking at, and really what you're wanting to find out.
Exactly.
So we could find out about oxygen atoms or just carbon atoms. That'd give us different answers.
Right. And it would help us to understand why different products are formed and why they are formed in the ratios that they are.
Great. So are we going to give them a problem to do themselves?
Why not?
Yeah, it's always fun.
It's always fun because it keeps them busy and lets us drink our coffee and sit there. So we started on the first problem from a mass. So let's kind of turn it around and start with the number of molecules.
Okay.
And see if we can work it out. So if we found out that we had 1.5, and this is your number, not mine, times 10 to the 16th.
Oh, that's a lot of molecules.
That is molecules of CO2. How many grams of CO2 does that represent? Well, if we look back to our little mole house, we can see that we can't get from molecules directly to grams. We have to go through moles. So to our T-chart, and we know the relationship is 1 mole over 6.022 times 10 to the 23rd molecules.
So on the chart, it looks like you're going from molecules to moles. Therefore, on the right-hand side, it's that you're dividing. So that's what's going to happen there. That's good.
So now our molecules are out. We're left with moles. We do the division. Handy-dandy calculator tells us it's 2.49, and we'll leave it there, times 10 to the minus 8 moles.
So that's not even anywhere near a mole.
No, really, really small.
So we should expect a gram amount that's pretty small too then.
Exactly. So we can see that if we have the number of moles and we want to figure how many grams we have, we simply take the molar mass.
And again, we're on the right-hand side, so we're going to multiply, right?
Right. So 44 grams over 1 mole of CO2. Our moles cancel out. And we're left with 1.096 times 10 to the minus 6.
Wow, that's pretty darn small. I don't think
Grams.
we could actually measure that in here.
No.
That's for sure.
No.
Well, I think that the students are going to have quite a large number of these problems to work on their own. So, good job, Mr. Burke. And I think the next time we look at this, we're going to develop some graphical organizers for it.
Sounds good.